Hey, Bicalc, Mr. Van Negas here, and I'm going to walk us through the multiple choice questions on our semester one final review. So to start with this first one, we're asked to identify which of these statements is false. So let's just go down the list. For option A, question is, does the limit exist as x approaches 2? Remember that a limit is always going to exist if and only if we can say that the left-sided limit and the right-sided limit equal and are the same. So let's take a look and see if that is true for these options. And I'm going to do that just by annotating my graph to be very efficient. So limit as x goes to 2. So as I'm approaching 2 from the left, that's along here. I approach that open circle. Remember, the limit is not necessarily have to be the same thing as the value of the function itself in order for it to exist. So I see that the function does approach the same value 2 as x approaches 2. So this exists. So that question is true. Looking at the next one, limit as x goes to 3 exists. Same thing. I'm just going to annotate red on my graph. All right, I see that I'm approaching that cusp. Cool. So at the point 3, 5, yep, that limit exists. It's true. Looking at the next one, limit as x goes to 4 of f of x exists. Here you can already see that's not going to be the case. As I approach from the left, the function goes to positive 2. As I approach from the right, the function goes to positive 4. So this one is my answer because it is absolutely false. Limit as x goes to 4 from the left equals 2, and that is not equal to the limit as x goes to 4 from the right. I'm going to be doing a lot more annotation and work just so you can see my thought process than I would necessarily want you to be doing on a real multiple choice section. Last thing to note, the function is continuous at x equals 3. Yep, we can see that that's completely true. There's no break there. It's a cusp, so it isn't differentiable, but it is continuous. So number 1 is C. All right, looking at this guy, simple derivative here, just requiring us to use our knowledge of the power rule. And actually, if I was feeling uncertain about this, maybe a good place to start would be to rewrite our function f of x as 4 times x to the negative 1. That's all I've done here. I've just rewritten the function, no changes, but I've rewritten it so that I can see that x has an exponent of negative 1. Important thing to remember from algebra. So now I apply my power rule. I get negative 4 times x to the negative 2 power plus 5. And just to make the computation easier, I'm going to rewrite that as negative 4 over x squared plus 5. Evaluating this at 2, f prime of 2 equals negative 4 over 2 squared plus 5. That's equal to negative 4 over 4 plus 5 equals negative 1 plus 5 equals 4. And that's option A. Moving right along to number 3, here we're going to have to use our quotient rule. Remember that for our quotient rule, say that our function f of x, if I can write that as some function u over v, then f prime of x is going to equal, remember my yodeling trick, the lowest part, low, d high, the derivative of the upper guy, minus high, upper thing there, d low, derivative of the denominator, over low squared. Low d high minus high d low over low squared. In this example, my numerator is u, that's 5 minus x. My denominator, v, is x cubed plus 2. So f prime of x going to equal my lowest guy, x cubed plus 2. D high, the derivative of u is just negative 1 minus high, 5 minus x. D low, just simple product rule. The derivative of my denominator is 3x squared plus 2 all over low squared. X cubed plus 2. squared. And FYI, guys, take a look. All of your answer choices, they all have something squared on the denominator. Do not waste your time doing needless algebra trying to expand x cubed plus 2. It's just a waste of time. What we do have to do, though, is a little bit of arithmetic on our numerator. Oops, that's going to be 5 minus x times, so that's 15 x squared plus 10 minus 3x cubed minus 2x. My numerator, denominator is unchanged. Simplify that guy one more time. Negative x cubed minus 2. Remembering my order of operations because I know I can never ignore that. And finally, combining my like terms. That gives me 2x cubed minus 15x squared made an error somewhere. Oh, I see where it was. Derivative of v, that should be 3x squared. There should not be a positive 2 there. My bad. Wondering where that 2x came from. Let's try that again. That will make that term of 10 go away as well. So I should finish out with negative 2x cubed minus 15x squared minus 2 divided by x cubed plus 2 squared. Very easy to make those little arithmetic errors. It's important that we're checking those. Answer choice C. Moving right along. For what values of the following, for which of the following values of x is f prime of x positive and increasing? All right, so let's explore what we're actually being asked here. Here's the graph of f. I want to know where is its derivative positive and increasing. So let's remember our relationships between the first derivative and the parent function. So if f prime of x is positive, that only occurs, as my double arrow, if and only if the parent function f of x is increasing. So I can use that right away to annotate my graph. I only am going to be looking for where my function is increasing. So that's like here in blue and here in blue. Everywhere else, function is decreasing. That's not really going to be of any interest to me. And then the second point, I want f prime of x to be increasing. So if f prime of x is increasing, that means my derivative, and remember my derivative represents instantaneous slope. So that's saying that my slope is increasing. My slope is increasing means that the function is getting steeper. So f of x is getting steeper as well as increasing. And a better way to say getting steeper using calculus, that means it's going to be concave up, right? If we're increasing and concave up, then our derivative f prime of x is going to be positive and increasing as well. And the only point, which I'll circle here in green, where we're both increasing and positive, or excuse me, concave up, occurs right there at point E. That rules out this part of my graph because it's concave down. Looking at number 5. Here I've got a table with some different values, velocities of a truck. I'm going to be using a trapezoidal sum, so I have to remember the formula for that. 3 subintervals which are indicated by the table. So as soon as I see that, I'm going to actually go right up here and annotate what are the lengths of each of my subintervals. So I've got from 0 to 0.5. So that first subinterval is 0.5. Drop that like this so that we kind of have a better picture of it. Second subinterval goes from 0.5 to 2. 2 minus 0.5, that's 1.5. And the last one from 2 to 3, that's a distance of 1. All right, so those are the lengths of my subintervals. And I want to know what's the approximate distance in miles, the time traveled from t equals 0 to t equals 3. That's the range that we've indicated here. All right, cool. I'm not actually really going to try and draw this one. That really wouldn't be a good use of my time. I'm going to recall, though, that the area of a trapezoid can be given like so. I'm going to call that height 1, my first height, plus height 2, my two y values here for the first interval, divided by 2. So the average of our two heights of our two y values times our interval, our interval width, excuse me. I'll call that my delta x. That's going to equal area of a trapezoid. All right, so I'm just going to call each of these area 1, area 2, and area 3. So the area of the first interval, that's going to be my first two heights, 20 plus 60 over 2 times delta x. I said that interval was 0.5 units long. So that is going to equal 20 plus 60 is 80, divided by 2 is 40, times 0.5 is 20. So it would very likely be a question that you could do without a calculator. Second one, interval, my two heights are 60 and 40, so 60 plus 40 over 2. It's 100, that's 50 over 2 times 0.5. So that's 25. Oh, whoops, not 0.5. My mistake. Should be 1.5. Got a different width. That's pretty important. All right, 50 times 1.5, that's 75. And finally, my third area, my last two heights, 40 and 30, divided by 2. That's 70 divided by 2 is 35 times 1. 35. Add these guys all up, and I'll get my total area, which is the whole area for all of these trapezoidal approximations for my function. And that's going to add up to 80, 100. That should add up to 130. Cool. Nothing else to it. Area is 130, so that is answer choice B. All right, looking at question number 6. I've got a function and I'm just trying to find its derivative, and this is only going to require me to use my knowledge of the chain rule, really, and the power rule and a trig integral derivative. Gosh. All right. So to start off, I see that I've got two functions. I'm adding them together, nothing weird here, but the whole quantity, that whole expression, x cubed minus cosine of x, is being raised to the 5th power. So I'm going to first need to use my power rule. I bring down my 5. That's left with x cubed minus cosine x raised to the 4th power, 5 minus 1. But I can't forget my chain rule. I must multiply now by the derivative of what's inside. Remember, we always work from outside in, outermost function, which in this case was something to the 5th power. And now we go after the innermost guys. So the derivative of x cubed minus cosine of x, power rule again, that's 3x squared. Derivative of negative cosine of x is positive sine of x. Cool. And I could try and multiply this all across, except I don't have to, because I look at my answer choices before I do anything, and I see that E is exactly what I have written there. So I'm good to go. All right, number 7, I flagged because it has a small typo. On your papers, if I remember correctly, it doesn't tell you that we're looking at time t equals 15 hours. I think it just says how many liters of oil are in the tank at time. That's not very helpful. We actually do need an end time for that. So I've corrected it in my paper here. You should be looking for how many liters of oil are in the tank at t equals 15. All right, looking at this whole thing, first big piece of information, a tank already contains 50 liters of oil at time t equals 4 hours. That will be important at the end. Oil is entering at a rate. The rate is measured in liters per hour, and time is measured in hours. here are our values of R and T up here in the table. We're going to use a right Riemann sum, so a right-handed sum with 3 subintervals indicated in our table. That's what's suggested by his phrase and data from the table. We want to know the approximate number of liters of oil that are in the tank at time t equals 15 hours. So to connect this conceptually, if I'm given a rate, remember that the area under a rate curve, all right, sort of, we think of this, that's going to be like my antiderivative, that's going to be like my integral. We're using a Riemann sum to do an estimate here, right? Net change is indicated by the area under a rate curve. So here's my rate. I'll actually draw out the curve this time. And if I look for if I find the area under that rate curve, that'll give me net change, or in other words, how much oil is in the tank or how much oil has been added from 4 hours to 15 hours. So to start, I'm just going to mark my intervals here. Got time from 4 to 15 hours, 7 and 12. This is not to scale, and that's fine because we're doing this pretty quickly. All right, and then I've got at 4 hours, we have 6.5. At 7 hours, 6.2. Again, not to scale. 5.9, and we'll say 5.6 is down here. The reason I like to sketch this out is because it helps me when I think, okay, I'm drawing a right Riemann sum. So that means I'm going to start at the right corner. Maybe I'll start all the way down here, actually. And the right corner of each of my boxes should be the thing that's just hitting my y value. So see how my first y value, 6.5, it's actually not really going to factor at all in any of my calculations because it's a right Riemann sum. I'm only drawing my rectangles so that their right corner, their upper right corner, is the thing that's intersecting my data points. Okay, now we can do the math. We could have done the math without drawing, but sometimes it's helpful to get our visual. All right, so this guy, I've got 3 areas, and they're as simple as could be. They're areas of rectangles. So the first one, like everything, like any rectangle, my area is given by length times width. So the width from 4 to 7 is 3. And my length, or rather I should say my height, is 6.2. So 6.2 times a width of 3. Maybe I'll annotate that just because I want to be pedantic, what my widths are. Okay. My second area is given by my height, 5.9, times my width, which is 5. My third area, my final height is 5.6. And my width is 3. Add those guys all up. And that's going to give me my total area under the curve from 4 to 15. Totally would want to have a calculator for this one, and I've already gone ahead and done the math. That should add up to 64.9. Now, at this point, you're probably thinking, Mr. Vanegas, there we go. There's our answer, but not so fast. We're asked how many liters of oil are in the tank at t equals 15. We've only measured the net change from 4 to 15 hours. I'm going to annotate that right there. Net change from t equals 4 to t equals 15 hours. But we were given a really important piece of information. We already started off with 50 liters of oil at time t equals 4 hours. So if we want to know how much oil is in the tank at 15 hours, we just add our initial amount, our starting amount, 50 liters of oil, plus the net change, how much oil was added from hour 4 to hour 15. Add those guys up, and we should get 114.9 liters. So our correct answer is C. Question 8, we've got a particle motion. And while it's not always the case that we want to distribute anytime we see some binomials here, I'm actually going to do that. So if I'm given my position function by x of t, a and b are just constants. It's probably worth noting. A does not equal B. We want for what values of t is the particle at rest? I would want to see this notation, this little annotation on everybody's paper. At rest. At rest means that my velocity is going to equal 0, right? If my position is given by my x of t, and I want to know, okay, I've got this particle in motion. When is it at rest? At rest just means its velocity is equal to 0. We've all studied up on particle motion, and we know that the derivative of our position function, if x prime of t equals position, the derivative is going to equal velocity. Right? The derivative of position gives us velocity, and that's what we're going to have to find next. So x prime of t, what's that equal? Well, like I said, it's not always a good idea to just jump into doing algebra, because if you don't have a goal, it's not helpful. But this derivative might be a little easier to compute if I first actually rewrite this in standard form. You should recognize that this is a quadratic, so I've got t squared minus at minus b times t plus a b. And I say that that's going to be helpful because when I do my power rule, x prime of t, I wind up with 2t minus a minus b. That equals my velocity function, which I'll call v of t. The a and b goes away because it's a constant. And the derivative of any constant is 0. All right, so I'm left with my velocity. I want to know, when is this at rest, i.e. when does this equal 0? So v of t equals 2t minus a minus b is going to equal 0. All right, at this point you might be thinking, okay, well, now what do we do? I've got 3 unknowns, but check out your answers. All your answer choices are in terms of t, a, and b. So here, I just need to do some pretty simple algebra. I'm going to add a and b to both sides to get 2t by itself. Divide both sides by 2. I should get t equals a plus b over 2. And that is given by answer choice B. Now, let's say we hadn't distributed and rewritten our quadratic in standard form. Let's say we had kept x of t as t minus a times t minus b. That's fine. We would have just done the same. When we take our derivative, we should get the same thing. I'm multiplying 2 quantities of x together. Maybe I'll just remind you, u and v. 2 quantities of t, not of x. So if I'm multiplying 2 functions of t together, that means I'm going to have to employ my product rule. So I could just take the derivative of my first guy. Derivative of t minus a is just 1. Derivative of t, that's 1. And the a disappears because it's a constant. So I'm left with 1 times t minus b plus first function t minus a times the derivative of t minus b, that guy. And that derivative is just, again, going to be 1. Derivative of t is 1. Derivative of negative b is 0. So I'm left with my velocity. Same thing as x prime of t. That's just equal to t minus b plus t minus a equals 2t minus a minus b. So our derivatives match, which they should. So we know that we have done the problem correctly. Looking at question 9, we are asked to evaluate a limit. So anytime you're asked to evaluate a limit, first thing you should probably do, direct substitution, see what it gets you. So the limit of e to the x minus 1 over x squared as x approaches 0. Let's just plug in 0 for x, giving me e to the 0 minus 0 minus 1 over 0 squared gives me 1 minus 1 over 0 gives me 0 over 0. Uh-oh, that is my indeterminate form. You all should recognize as soon as we do that, as soon as we see that direct substitution yields indeterminate form, we're going to need to use L'Hopital's rule. If this were an open response question or a free response question, it would make you write out by L'Hopital's rule. And we'll do that here just to be in the habit of it in good practice. So by L'Hopital's rule, those three simple words will be the difference between getting full points and losing points on an FRQ. And I know that L'Hopital's rule just tells me that this limit, since I got an indeterminate form, when I try direct substitution, it's going to be equal to the limit of the derivative of the numerator, which in this case is e to the x minus 1, over the derivative of the denominator, 2 times x. No quotient rule, nothing funny here. All that we're saying is that limit x goes to a, my f of x over g of x is going to equal the same exact limit of the derivative of the numerator over the derivative of the denominator. Okay, so now back over here, let's try direct substitution again, plug in for 0, so that gives me e to the 0 minus 1 over 2 times 0. Uh-oh, I think I know where this is going. Gives me 1 over 1 minus 1 over 0. Gives me 0 over 0. Indeterminate form. Again, we had it in our first step. We have it in our second step. That's fine because we can use L'Hopital's rule again. So now I'm saying that the limit of e to the x minus 1 over 2x by L'Hopital's rule a second time is going to equal the limit as x goes to 0 of the derivative of the numerator, which in this case is just going to be e to the x over the derivative of the denominator 2. I'm going to write by L'Hopital's rule one more time, just because I want to be in the habit of it and justify that. All right, let's try direct substitution one more time, see if it works. Notice how I'm being very careful about when to use my limit notation. I only can drop it when I start to evaluate something directly. Plugging in 0 for x gives me 1/2. So at the end of this long crusade, I should get option D. The limit equals 1/2. All right, now I've got this function, g of x, k is a constant. Now we have to solve for k. For what value of k? This is the guy we're solving for. That's my unknown. Important part of our math plan of attack is identifying our unknowns. And we're saying, does g have a critical point? I would want to see this annotation on everyone's page. Remember, critical points occur when my derivative is equal to 0. And we're given at the point x equals 2/3. So here we're not trying to solve for any value of x, we're trying to solve for k. And one of our givens, another important part of our math plan of attack, is 2/3. Okay. Oops. So if we know that critical points only occur when our first derivative is equal to 0, let's find that first derivative. K prime of x here, I've got two functions of x. I've got x squared and e to the kx. So I'm going to have to use my product rule. Remember that if I've got some function g of x equal to u times v, where both of these are functions of x, that means that their derivative is going to be u prime v plus u v prime. All right, doing my product rule, that's going to give me derivative of the first guy, x squared, that's 2x, times e to the kx, no derivative taken, plus the first guy, unchanged, x squared, times the derivative of e to the kx. The derivative of e to the anything is just itself, e to the kx, but I've got to do my chain rule here because I'm raising e to a function of x, k times x. Sneaky, but there's hidden in there another function. The derivative of k times x, k is just a constant, it's going to give me k, right? Because I can just do simple power rule there, see that x to the 1, but I should also know automatically the derivative of any function where I just have a constant times x is going to give me the constant itself. All right, here's my derivative. Let's simplify it a little bit. I'm going to try and see what I can factor out here. I'm going to factor out x and e to the kx. Actually, let me just rewrite it in a sort of neater form first before I do any factoring, because that's a good way to make an error. Kx squared e to the kx. Okay, that's a little bit neater. Now I'm going to factor out x and e to the kx. That should leave me with 2 plus x. That's my first derivative. All right, I'm happy with this so far. Whoops, except for my k, there should be a k there. That's why it's always good sometimes to pause and take stock of your work for just a second. All right, so now I think I've got everything that I need, and I said I wanted to figure out for what values of k will I have a critical point at x equals 2/3. So critical point, that means our first derivative has to equal 0. Let's do this on a new line. And I said when x equals 2/3. So let's plug in 2/3 for x. 2/3 e to the k times 2/3, 2 plus k times 2/3. And a critical point occurs when my first derivative equals 0. Now you'll see why I factored here. It's a very good thing to do in advance if I'm anticipating I'm going to be finding critical points, because I can see right away e to the k times 2/3. No matter what k is, that function will never touch the x-axis. It's a very important fact. If you know what the graph of e to the x looks like, you should know that it is exponential. It's never going to quite touch our x-axis there. So this could never be 0. So I can divide by it, right? I can divide by anything that's not equal to 0. And that's going to leave me with 2 plus 2/3 k equals 0. And now this is just a very simple algebra problem. Time and again, calculus just evolves into very easy algebra problems. All right, multiplying by the reciprocal gives me times 3/2 times 3/2 gets k by itself. That's -2 times 3/2. So k just equals, my 2's cancel out, -3, which is answer choice A. Moving on to question 11. All right, I've got f function given by this here. What is the approximation? We are going to do some linear approximation for f of 1.5 if we use the tangent line at x equals pi over 2. So right away, whenever I see linear approximation, I actually like to write out the form for that. We might have used a slightly different form. That's okay. I like to use this one myself because it points out sort of what my unknowns are. Namely, I'm going to need to look for a y1 and an x1 and an m. Well, x1 and y1, those guys just refer to my nearby point. A nearby point to the thing I'm trying to estimate, f of 1.5. And I'm already given that, right? I say using the line tangent to the graph at x equals pi over 2. So x1 is going to just equal pi over 2. How do I find y1, you may ask? Well, you're given the function f of x. So if our nearby point is at x1, I should know that y1 is just going to be given by my function evaluated at x1. And in this case, that's 2 times the cosine of x, which is pi over 2, plus 1. You all should know that cosine of pi over 2 is equal to 0. So this is just 0 plus 1 equals 1. So I'll write these guys up here. x1 equals pi over 2. y1 equals 1. Now, as far as m, we should recognize that's just our slope. Written this in point slope form for a reason. How do I find a slope? Well, we all know that slope, instantaneous slope, is just the same thing as my derivative. And specifically, I want the instantaneous slope at my nearby point. So that's going to be at f prime of pi over 2. But let's just start by calculating what f prime of x is. Let's not get carried away just yet. So the derivative of my function, derivative of 2 cosine of x, cosine is negative sine of x, that's -2 sine x. And my constant just disappears from my derivative. All right, So my derivative f prime of x is negative 2 sine x. Let's evaluate that at pi over 2, my nearby point. That's how I'm going to get my slope. Maybe I'll write that over here. M is going to equal f prime of pi over 2, negative 2 sine pi over 2, which is going to equal negative 2 times 1. Another thing we must all know because we all have our unit circle memorized. So m equals negative 2. I've got my values of m, I've got my values of x1 and y1. So I can construct a really nice equation here, y minus 1 equals negative 2 times x minus pi over 2. All right. Now I want to know what's the approximation for f of 1.5. Time for this guy to come in handy. So that is going to become my x value at the very end here. So I've got y minus 1 equals negative 2 times 1.5 minus pi over 2. And you might be thinking, oh no, got to reach for that calculator, but you don't. All of our answer choices are given in an exact form. So I'm just going to say this is y is equal to negative 2 times 1.5 minus pi over 2 plus 1. I'm going to bring that work up here. I distribute my negative 2, so I get negative 3, negative 2 times 1.5 plus pi plus 1. That should equal negative 2 plus pi. Negative 2 plus pi, or pi minus 2, is given by answer choice C. Number 12 is a related rates problem, everybody's favorite. You've got a lot of information to work with here, so let's get to it. We're given it that we've got an isosceles, right triangle. As soon as I see those words, I'm just going to draw one over here so that I've got a picture. And we're calling the lengths of our side S. So there's S, and here's my hypotenuse. Maybe I'll call that H, or better yet, I'll call it C. There's my hypotenuse of length C. We're told that we've got an area. We could have figured that out ourselves, but it was nice of them to give us that. Area of that triangle is 1/2 s squared. And we're told at the instant when s equals root 32 centimeters, the area of the triangle is increasing at a rate of 12 centimeters squared. So this is the thing I want you all to really take a note of. When I see quantity, area, is increasing, changing at a rate, we should recognize that we're talking about a derivative. So I'm going to add that information over here, just off to the side, when s equals square root of 32. The derivative of a, the change in our area over the change in time, that's really important. That's indicated by our unit centimeters per second, square centimeters. That's our area per second. That's time. So the derivative of our area, the rate of change of our area with respect to time, is equal to positive 12. It is increasing at a rate of 12 square centimeters per second. Now they're asking, at what rate is the length of the hypotenuse increasing? So again, another rate. So that's our unknown. And so we're trying to find the derivative of our hypotenuse. I think I called that C. dc dt is our unknown. What is the rate of the length of the hypotenuse in centimeters per second at the same time when s equals root 32? And the derivative of our area is equal to 12. All right, well, here's something that we should note immediately. We're trying to find the derivative of the rate, or the rate of change of our hypotenuse with time, right? dc over dt. There's no place for c in this formula. And that should be your first big clue that I'm going to need a different formula here. So what triangle formulas do we know? Well, I don't know a ton off the top of my head, but I do know my Pythagorean identity here. The Pythagorean theorem. I know that a squared plus b squared equals c squared, where A and B are the legs of a triangle and C is the hypotenuse. And here we're told that the legs are the same. It's an isosceles right triangle. So they're both S. Let me just change this to S squared plus S squared equals C squared. All right, I've got a formula involving C. I've got a formula involving A. Let's take some derivatives. Now we actually get to do our calculus. I don't have a huge preference. I don't know that organizationally it makes more sense to take one over another. I'm going to start maybe by taking the derivative of area, dA over dt. I'm taking the derivative of every guy here. Start by just saying this is d over dt of area equal to 1/2 s squared. All right. So A is just a lone variable, no exponent or anything like that. So that just becomes dA over dt is equal to 1/2 times, doing my product rule, derivative of s squared. That's going to be 2 times s. And I need to do my chain rule because s is also changing with time. So ds dt. So I have dA over dt equals 1/2 times 2 is just 1. S times ds dt. I'll come back for you in a minute. But here's one of my derivatives. Now let's take the other one. Let's do the derivative of this guy. If I take the derivative of my Pythagorean guy, again, with respect to time, s squared plus s squared equals c squared. Taking the derivative of everything, that gives me 2s. Oh, and I guess I could have actually combined this. Let's make this a little easier on ourselves, guys. S squared plus s squared, that just equals 2s squared. So when I take the derivative, I should get 4s times ds dt equals 2 times c times dc dt. All right, now I can actually see where there's a dc dt, and I circled that up here because it's what I'm trying to find. And with all these variables, I'm very likely to get confused. So I'm going to change this formula slightly so that I have dc over dt equals 4s times ds dt divided by 2c. So dc over dt is going to equal 2s times ds dt. Whole thing is divided by c. All right, cool. This tells me a few really important things. I'm going to leave this guy boxed for the time being, because in order to get dc over dt, I need to know what s is at this particular time, which I already do. That was one of my givens. I'm going to need to know what c is. I don't know what that is at that time, but I can figure it out. And I need to know what ds dt is. That's a key one there. I've got a formula for ds dt in terms of things I already know. So let's just start solving one thing at a time. I'll go with I'm going to write this down here in red, new color. Solving for dc over dt, that's going to equal 2 times s, which I said in my givens was square root of 32, divided by c. First thing that I don't know yet. So let's figure out what c is. I'm going to come over here to do this. We said originally with our Pythagorean guy that s squared plus s squared equals c squared, or 2s squared equals c squared. So let's do that in the margin here. 2s squared equals c squared. What is s? We've already said it, root 32. So 2 times square root of 32 squared equals c squared. That's 2 times 32 equals c squared. 64 equals c squared. Taking the square root of both sides, c equals 8. Beautiful. All right, so down here, I can replace this with 8 instead of c. All right, making some progress. And now I need to solve for ds dt. All right, so I've got a formula for dA dt equals s times ds dt. Let's rewrite that guy since I'm trying to solve for ds dt. That's going to equal dA dt times 1 over s All right, I was told in my givens that dA dt equals 12. It's 1 over s, which is just square root of 32. So that leaves me with ds dt equals 12 over the square root of 32. Okay, so there's ds dt, there's my c. All right, all the way back down here. Last thing I need to multiply by was ds dt. And we just said that ds dt is equal to 12 over the square root of 32. Now I get some lovely cancellations of square roots cancel out. I'm left with 2 times 12 over 8. That's 24 over 8. So the rate of change of my hypotenuse, C, with respect to time is 24 over 8, which is equal to 3 centimeters per second. Whew. That was a heck of a lot of work for one answer. The final, make sure that you're pacing yourselves. It's a great question if you've got the time to get for it. Would be okay to leave this one for the end after you've answered the easy ones. All right, looking at question number 13. Slightly easier now, actually significantly easier. I'm given this function's derivative actually already. I don't know what y is, but I know that dy dx equals x to the fourth minus 2x cubed plus 3x minus 1. We're trying to find the third derivative at x equals 2. So to find the third derivative, I first need to find the second derivative. So d2y dx squared, remember that notation, is equal to 4x cubed minus 6x squared plus 3. This is just a bunch of product rule. We'll do it one more time. D3y over dx cubed. The third derivative is equal to 12x squared minus 12x. Easiest thing in the world. Cool. And now I just want to figure out what is that at x equals 2. So d3y over dx cubed evaluated at x equals 2 is going to equal 12 times 2 squared minus 12 times 2. So that's going to give me 48 minus 24 equals 24. Short and quick. Looking at number 14, we need to remember our inverse derivatives. All right, not going to get into how we derive that because we've already learned that in class. This would be a good one to either refresh yourself on the derivation or commit it to memory. But we should all remember, all right, we're given here that g of x is my inverse. So that equals f inverse of x. And we should remember that if that's the case, then the derivative of that guy, the derivative of my inverse, is going to equal 1 over f prime, the derivative of f of the inverse at that point. If I wanted to, I could replace f inverse of x with g of x, but inverses sometimes confuse us. So just a reminder, this would be a very good thing to jot down. Inverse, that just means that x and y are swapped. So for example, let's say that I had a little table of values x, y here, and I am given that information. It's an important thing to annotate. F of 0 equals 1. So if I put in my x value for 0, my y value is 1. I'm going to change y to f of x, actually. I'm doing that because for my inverse function, g of x, my x and y values are swapped. So at x equals 1, g of x is going to equal 0. And that's pretty important because we're asked to find g prime of 1, the derivative of my inverse function evaluated at 1. All right, so let's get down to that g prime of x we said was equal to 1 over f prime of f inverse of x. So f prime, f of x, we said f of x is equal to 2x plus 1 cubed. F prime of x, some easy power rule stuff, is just 3 times 2x plus 1 squared. Do not forget your chain rule times the derivative of 2x plus 1. So f prime of x is equal to 6 times 2x plus 1 squared. All right, so g prime of x is going to equal 1 over f prime was 6 times 2x plus 1 squared, and we're evaluating it specifically at f inverse of x. So maybe to make this as easy to read as possible, I'm going to say this is equal to the derivative of g is equal to 1 over f prime of f inverse of x. All right, that's f inverse of 1. We said again, our x and y values are swapped. So if we're told that f of 0 equals 1, then f inverse, that's implying that f inverse of 1 equals 0. So that's going to be 1 divided by the derivative of f prime evaluated at 0. Which is going to be 1 over, I said f prime of x over here, 1 over 6 times 2 times 0 plus 1 squared, which is just 1 over 6 times 1 squared, which is just 1/6. Not too bad. All right, question number 15, we've got a graph of f prime, the derivative of our function f. Which of these statements are true? All right, let's look at them one at a time. F has a relative minimum at x equals 3. All right, as soon as we see that, I want to see this annotation on your page. If f has a relative minimum, that occurs if and only if f prime of x changes from what to what? Well, let's think. F prime gives me slope, right? Derivative gives me instantaneous slope. So if I've got a maximum, that means my slope is changing from positive to negative, right? Relative max, I go from having slope which is positive to slope which is negative. In other words, f prime changes from positive. Oh, whoops, did I say max? I meant to say min. Oh my gosh, let's erase that. That's not helpful. If we want a minimum, let's try that again. This is why I like to draw pictures. Here's my relative minimum. That means that my slope goes from negative to positive. So if f has a relative minimum at x equals 3, that means f prime of x has to change from negative to positive at x equals 3, negative 3. So does that occur? Well, here's negative 3, and here's f prime. It's negative here, and it's positive here. Cool. So it looks like that's a true statement. We must have a relative minimum for f at x equals negative 3 because f prime is changing from negative to positive at x equals negative 3. All right, what about the second one? F has a point of inflection at x equals 2. All right, what does a point of inflection mean? Well, a point of inflection means that in our parent function, we're going to see a change in concavity. In our second derivative, we're going to see a change in sign. In our first derivative, f prime of x should change direction. Now, whether it changes direction from increasing to decreasing or decrease to increasing isn't going to matter. It'll give me a point of inflection either way. So f of x changes direction. In other words, increasing to decreasing or decreasing to increasing. Doesn't matter which one. They'll both give me a point of inflection. Okay, at x equals -2, does that occur? Here's -2. I don't think that's the case because we're increasing to the left of -2. There's -2. Maybe briefly we hit a horizontal tangent line, but we continue to increase. So f prime is just increasing. There's no change in direction. So statement 2 is false. Last one, graph of f is concave down. All right. So if we're concave down, we know that means our second derivative is negative. If that's true, that's going to mean if and only if this only occurs if f prime of x is decreasing, right? If f prime of x is decreasing, then f double prime of x will be negative, and that all connects to the parent function being concave down. So is f prime of x decreasing on this interval from 0 to 4? All right, here's 0, here's 4. Function sure looks like it's decreasing that whole time for me. F prime is decreasing that entire interval. So this one is true. So 1 and 3 are true. Answer choice E. All right, looking at 16, I think this is the first one we actually are going to need to use a graphing calculator to solve. So we're told f prime of x equals this expression, then f has a local maximum. Again, I want to see this annotation. F has a local maximum if and only if, 1, f prime of x is 0, but 2, more importantly, we're changing. Changes from positive to negative. If you have trouble keeping them straight, as I obviously do, sometimes it helps to sketch. That's what a relative maximum is going to look like. Here my slope is positive, here my slope is negative. All right, so let's graph this guy. I went ahead and graphed this in Desmos. You, of course, must be using your graphing calculator because you won't have Desmos on your final. So let's take a look at this function. Where is our graph going to be changing from positive to negative? All right, I've got f prime of x. Remember, this is f prime of x here. I've just had to call it y. That equals, here it's negative, going from negative to positive. That's not what we want. That'd be a local minimum. It's all positive here. At this point, f prime of x is going from positive values to negative values. That is at 0.35, also not good enough because you need 3 decimal places. Another reason you cannot use Desmos. Answer choice C, 0.350. Remember, on your graphing calculators, you can very easily hit, I believe it is second and trace. That will open up the calculation menu once you've got your function graphed. Remember that you need to have your window at a reasonable rate so that you can actually see an image. But if you press second and trace, you can then calculate for where all of your zeros are going to be. All right. And we would know that just from looking at the graph, I only care about the 0 right here because my graph of f prime is going from positive to negative at that point, indicating a local min. That's care of 16. Let's look at 17. This one's actually an algebra 2 question. We're asked if this is our function, it'll have vertical asymptotes where? Remember, vertical asymptotes, places where my graph kind of blows up either to infinity or negative infinity, and I can never touch that line. We could do this a couple of ways. We could graph this in our graphing calculator, which you will have access to for all parts of the final. We could take the derivative and see where that's undefined. That is going to indicate a point that's not differentiable, which would be a vertical asymptote in this case, because I've got a rational function. But I'm actually going to do a little trick from algebra 2. I'm just going to factor my numerator. I'm going to factor out this x, because as soon as you take a look at this function carefully, you should recognize that my numerator and my denominator look really similar. What do you notice there? Factoring an x out of the numerator, I now have the same thing on my numerator and denominator. I could factor this further into x plus 3 and x minus 1 on the numerator and denominator if I wanted to. I don't have to, but if I were to, it might make a little bit more sense what I'm about to do next. Since I've got the same thing on the numerator and denominator, and I am multiplying the same thing, not adding, but multiplying the same thing on numerator and denominator, I can cancel these guys all out. They disappear. And in fact, if you graph g of x, it'll look just like the function x. That technically means that we've got a hole. If you remember, we'll have a hole in our graph, a discontinuity at x equals -3 and x equals 1. But those aren't asymptotes. Holes are not vertical asymptotes. There are no vertical asymptotes here because there's no value of our function that'll make our denominator equal to 0 that won't also make our numerator equal to 0. Function g has no vertical asymptotes. Pretty cool. All right, number 18. At what value does x of x does f attain its maximum value on this closed interval if we're given that information? This is probably, I would say, maybe the hardest question on the multiple choice packet. Normally, we would just use our closed interval test and find our critical points and then evaluate the critical points and the endpoints using the original function. But we are not given the original function. All right, we're told that f has this first derivative, but we're not told what f is. And we don't know how to compute the antiderivative for this. So this is pretty tricky. To make it easier for us, since it's obviously a calculator question, let's go ahead and graph our first derivative. So I've done right here. And we're only interested, I'm going to zoom in on the interval from 0 to 2. Not interested in anything else. All right, so I'm going to observe the following. At my endpoint here, 0, I don't know where my function is, but I can see that the derivative is positive. And I should remember well that if my derivative, f prime of x, is positive, that means that f of x is increasing. So if f of x is increasing to the right of 0, there's no way that 0 can be its absolute maximum, because any point here along this interval to the right, we've been increasing. We continue to increase and increase and increase. F prime of x is still positive all the way through here, through here, through here, through here. That means that f of x is just going to be increasing. It's going to be growing. So this behavior continues to happen until we hit 1.465. All right, at that point, we're going to have a horizontal tangent line because our slope is going to equal 0. So I'm actually going to just make a little rough sketch here. I do very much mean rough. So my derivative looks something like this. Spike up, go back down, and then it's going to come up, I think, briefly again, yeah, to about the same point at x equals 2. So there's 2. There is 1.465. And that other 0 occurs at 1.845. All right, so check this out. If my function's derivative, f prime of x, is positive on that interval, that means that f of x is increasing. So we're increasing from that whole time period. I don't know, again, where we've started. Maybe we're really negative, really positive, somewhere in the middle, who knows? But I know that from 0 to 1.465, this thing is just really blowing up. And then at 1.465, f prime of x is equal to 0, which means I'm going to have a horizontal tangent line. I'm going to label this as my graph of f of x, and this as f prime of x. Again, I'm just doing some rough sketching here to help me visualize. All right, on this interval down here from 1.465 to 1.845, I see that my first derivative is negative. Remember that if f prime of x is less than 0, it's negative. That only occurs when f of x is decreasing. Must mean that f of x is decreasing. So from this interval here, all the way from 1.465 to 1.845, we're decreasing. Maybe we seem to decrease by quite a lot, actually. It gets pretty severe there. Have a little inflection point right around here. And then I don't know how far down I've gone exactly, but I can see that I'm going to be getting pretty negative. Let me draw this as a nice continuous curve there. And then again, a horizontal tangent point right there at 1.8465. Finally, for there up to 2, we see that I'm increasing again. Here's where you really have to be wise, though. Notice that my interval of increase here, f prime of x, is also increasing here. But notice that I increase by this much in that amount of time. You might say, well, hold on, Mr. Matthias, you get to the same y value anyways, so you must eventually, how can you tell which one is higher? But realize that what this is really saying is that our function was increasing for all this time. Here, at this point, it was increasing the most. It was maybe the most vertical. It was the steepest increase, but it was consistently increasing from 0 to 1.465. This is a much shorter interval. Sure, we start going faster sooner. We don't have that low increase at the beginning. We kind of go straight up from the start, but we wouldn't be able to reach the same height after such a short interval. All right, even though we reach the same slope eventually, in this case, we continued to accelerate, or we continued to increase. Our slope continued to be positive. The function continued to increase, and the function was increasing before that. So that means that at f of 2, the end of our interval, we're going to be lower than an absolute max, which occurs at 1.465. It's a pretty difficult one, but the rest are going to be a lot easier. All right, 19, another typo here. It's going to be a typo in the answer choices. I have made the change in mine. We'll see that when we get there. This one's a refreshing, easy one. So we're given this function f of x equals 300x minus x cubed. And we want to know on which of the following intervals is f increasing. Well, as we have been saying consistently, if f is increasing, that only occurs when f prime of x is positive for any continuous and differentiable function. All right, so I'm going to find my first derivative. Easiest power rule in the world gives me 300 minus 3x squared, which is just going to be equal to 3 times 100. I love to factor my derivatives when it makes my life easier. All right, cool. So there's my first derivative. I want to know where is that positive. At this point, I could graph it on my calculator. That's fine. But I want to do this one analytically because I actually think it's faster than what it'll take to graph it. So in order to figure out where my function f is going to be increasing, that means I need to know when is my first derivative positive. In order to know when my first derivative is positive, I'm actually going to start by finding out where is it equal to 0? Where are those critical points? Then I'm going to construct myself a sign diagram. So where is this guy equal to 0? Well, I know I can factor out my 3 at this point. 100 minus x squared equals 0. Means x squared is going to equal 10. So I've got, x squared is going to equal 100. And x is going to equal plus or minus the square root of 100. And that is just 10. Cool. Let's draw the sign diagram. So here's f prime of x. Here's 10. Here's negative 10. All right, let's check in the middle between negative 10 and positive 10. Just going to do some workout over here. Let's try the point 0. It's an easy one. So at the point x equals 0. I could plug that in for f prime of x, which equaled 3 times 100 minus x squared. But I should recognize right away that's just going to equal 300. It's going to be a positive value. So f prime of x is positive here, which means f of x is increasing in this range. All right, let's try something else. Let's just keep life easy and let's try 11. All right, plugging in 11 to my function here, f prime of 11 is going to equal 3 times 100 minus 11 squared. 11 squared is just 121. I'm not actually going to do any more arithmetic at that point. I'm pretty lazy. 100 minus 121, 100 minus something bigger than 100 is going to be negative. So I know that I'm going to have a minus sign here. And let's try negative 11. Recognize that I'm squaring something. X squared negative 11 squared is going to be a positive 121. So f prime of negative 11 is going to equal the same thing, which is just less than 0. Don't care what it is, just so that I know it's less than 0. All right, so on these two intervals here, f of x is decreasing, and my only intervals of increase, my only intervals of increase for f of x are going to occur right here. Now, on your paper, answer choice B is the correct answer here, but on your paper, I believe it shows square brackets, and those are wrong because I don't want to include these endpoints, because what is the derivative at negative 10 and 10? It's 0. We're not increasing if our derivative is equal to 0. Remember, the picture is always if our derivative is equal to 0, we either got a relative min or relative max or a saddle point. Never is the function increasing or decreasing when its derivative is 0. It's just stuck. It's the point before any of that changes. So I'm just going to erase this out of the way. So your correct answer should be B, and I want you to make sure that you've changed it on your document to indicate that those should be open parentheses because it's an open interval. All right. Looking at number 20, another typo there. Sorry about that, guys. It's the last one. This should say f of x times g of x. I think on yours it may have said f of g of x, and that's actually incorrect. I want to know when f times g. I don't want to know what f times g is equal to, the derivative of that. All right, pretty cool relationship here right off the bat. F prime of x is equal to g of x, and g prime of x is equal to f of x. What's the second derivative of that product? F of x times g of x. All right. So I'm looking at f of x times g of x, taking its first derivative. That's going to give me product rule here, f prime of x times g of x plus f of x times g prime of x. And if I wanted to, I could make some changes. I could say, well, all right, f prime of x is equal to g of x, and g prime of x is equal to f of x. So if I wanted to, I could actually say that this is just equal to g of x times g of x plus f of x times f of x, which is just going to be g of x squared plus f of x squared. Taking my derivative one more time. Being very great with my annotations here. Let's use my simplified form here. Product rule means I've got 2 times g of x times g prime of x plus 2 times f of x times f prime of x. And again, using what we've learned up here, g prime of x is equal to f of x and vice versa. So that's going to equal 2 times g of x times f of x plus 2 times f of x times g of x. I can rearrange my variables in any order because multiplication, associative. So that's 2 times g of x times f of x plus 2 times g of x, f of x. Those add together and equal 4 times g of x times f of x. If you were totally lost on this problem and you wanted to like do a little sanity check, you could check each of these answer choice and you'll actually see that these two and these two, that when we do them all out, we're going to see that they come to equal each other. Let's look at the more complicated ones. F prime of x and g prime of x. F double prime of x and g double prime of x. That's the same thing as f prime of f prime of x, or rather the derivative of f prime of x. We said f prime of x is equal to g of x, right? So if I take the second derivative, let's actually evaluate that. If f prime of x equals g of x, then f double prime of x is going to equal g prime of x, but g prime of x equals f of x. So f double prime of x equals f of x. And let's do the same thing for g prime. G prime of x equals f of x. G double prime of x equals f prime of x, which just equals g of x. So the second derivative of g just equals the original function g. So that means that this guy, f double prime of x times g double prime of x, is just going to be g of x times f of x, which we can see is repeated in answer choice E. So those guys are incorrect. And I could do the same thing. Maybe I'll do that in orange. For answer choice B, if I'm told that g prime of x times g of x plus f of x times f prime of x, but g prime of x is going to be f of x, right? So f of x, g of x plus f of x times, and f prime of x is g of x. That's just going to equal 2 f of x, g of x, which again is repeated as answer choice D. So we've confirmed that C is the correct answer for number 20. Let's move on to 21. This one is a lot of functions, so let's try and keep them all straight. G of x equals f of x squared. F of x equals h of x cubed plus 1, and h prime of x equals 2x plus 1. What is g prime of x? So to keep everything straight, I'm just going to write them all out. So g prime of x will have to equal f prime of x squared. So to make that a little bit easier on ourselves, let's actually make a note of something over here. I'm gonna do 2 columns here. I'm also gonna corner that stuff off so we don't confuse ourselves. F of x equals h of x cubed plus 1. That means that f of x squared is going to equal h of x squared cubed plus 1. And that's pretty important. It's going to make life pretty easy. Notice how all I did was just replace an x squared wherever I saw an x in the function there. So that's h of now x to the 6th power plus 1. So f of x squared equals h of x to the 6th plus 1. Okay, you might be saying, so now what? How does that actually make things any easier? Well, it means that g prime of x equal to f prime of x squared is going to equal h prime of x to the 6th plus 1. And we also know that h prime of x is equal to 2x plus 1. So to finish this out, let's just do h prime of x to the 6th plus 1. Anytime I see an x in my expression for h prime of x, I'm just going to replace it with x to the 6th plus 1. That's 2 times x to the 6th plus 1 plus 1. Remember, this whole thing is equal to g prime of x. So g prime of x equal to 2 times x to the 6th plus 1 from my h prime of x formula gives me 2 times x to the 6th plus 2 plus 1. 2 times x to the 6th oh, whoops, I did a mistake here. I'm sure many of you watching probably saw it. I forgot to utilize my chain rule. After 20 of these, your stamina takes a hit. So sure that you remember that on your final and be practicing this for stamina. All right, so my error was that h prime of x to the 6th plus 1, man, I was so close too. It's going to equal, just like we said, 2 times x to the 6th plus 1 plus 1. All of that jazz is unchanged. But I now need to multiply that by the derivative of what's inside. X to the 6th plus 1. So that is just going to be 6x to the 5th. Let's isolate that guy. All right, so rewriting this here, g prime of x equal to h prime of x to the 6th plus 1. It's going to equal 2 times x to the 6th plus 1 times 6x to the 5th. That is going to equal 2x to the 6th plus 2 plus 1, whole quantity multiplied by 6x to the 5th. That is going to equal 2x to the 6th plus 3 times 6x to the 5th. That is going to equal 12x to the 11th. I add my exponents. I multiply those guys together plus 18x to the 5th. Answer choice E. Whew. All right, almost done. 22, particle motion. Here's my position. Actually, my velocity. Velocity is given by v of t. What is its acceleration? Annotation that I would want to see from all of you is that acceleration, we know that a of t is just equal to the derivative of v of t, right? V prime of t equals a of t. The derivative of velocity is your acceleration. And we want to find what? We want to find the acceleration of the particle at time t equals 4. A of 4 equals what? That's what we're looking for. Love to see that kind of annotation, your unknown, important part of our math plan of attack. All right, so let's calculate what v prime of t is. So 3 is a constant, goes away, don't care about it. It's going to equal 4.1 times the derivative of cosine is negative sine of 0.9t. And then by my chain rule, I've got to multiply by the derivative of 0.9t, which is just 0.9. Using a calculator, it's obviously a calculator question, just looking at the answer choices. That is going to give me negative 3.69 sine of 0.9 t. And our acceleration, which is just equal to our derivative of velocity. So a of 4 is equal to v prime of 4, which is equal to negative 3.69 times the sine of 0.9 times 4. Again, using my calculator, I should get 1.633 units per second squared. Answer choice C. 23, I'm given an interval and I've got a derivative, a first derivative here, given by that guy. Which of the following are all intervals on which the graph of f is concave down? Great question. So if f is concave down, that means our second derivative is negative, but we're given a first derivative. So that means if f is concave down, our first derivative, f prime of x, must be decreasing. Or we could say, and f double prime of x is less than 0. Now I did this, we can do this two ways. We can graph f prime of x and take a look and see where it is decreasing. You're going to have to use your calculator to find the max and the min to see what those intervals are precisely. I chose to just find f double prime of x because it's actually not that hard to do. If our first derivative, f prime of x, is e to the x to the fourth minus 2x squared plus 1 minus 2, f double prime of x is going to be same thing, e to the x to the fourth minus 2x squared plus 1. Negative 2 disappears, and I need to use my chain rule, so I multiply that whole guy by the derivative of the exponent. So x to the fourth, that derivative is 4x cubed minus 4x, and that's it. All right, not so bad. At this point, I want to graph it. Analytically trying to figure out where this is equal to 0 is also an option. I know that if I were to set this equal to 0 and then try and figure out where it's negative, that's totally fine. I know that this guy here can never equal 0. So that's out of the running. So I'm left with 4x cubed minus 4x equals 0. Factoring out a 4x, I'm left with x squared minus 1. 0, gonna bring that over here. 4x times x plus 1, x minus 1 equals 0. So x has to equal -1, 0, or 1. If I were to construct a little sign diagram for f double prime of x, 0, 1, -1. This is why I say I want to consult my calculator at this point, because there's really not an easy way. I mean, I know that this is always going to be positive. So I suppose I could use what I've got here and test some values. Just do that real quick. If I do positive 1/2, I should see that that's going to give me a negative value because of the x minus 1. 1/2 minus 1 is going to give me a negative value. Everything else is going to be positive. So I expect that this will be negative here. All right, cool. So that means that we're concave down from 0 to 1. Looks good to me. How about if I try -1/2? Nope, that's going to give me something positive. Again, I'm only looking at this form of the second derivative. Could definitely have organized my work a little bit neater over here. Let me try and redo that so that we can actually follow along with that. I said in its simplest form, f double prime of x equaled 4 times x plus 1 times x minus 1. All right, working with that derivative now, that second derivative. If I plug in -1/2 for x, that's going to give me a negative value here. Nope, that's going to give me a positive value here of 1/2, -3/2, -2, a negative and a negative. It's going to obliterate, so it's going to be positive on that interval. If I choose something greater than 1, let's say 2, everything is going to be positive. I'll have 8, 3, and 1, positive there. Let's try -2, something equally easy. Let's say, all right, that'll be -8, excuse me. -1, -3, 3 negative values, all negative. Cool. So I should see at this point then we said decreasing, f prime of x is decreasing, or f double prime of x is less than 0. So that occurs. F of x is concave down. F double prime is negative. And that occurs on the intervals negative infinity. Oh, whoops, I'm sorry, negative 1.5. Got to be careful for what our interval is that we were even looking at. So that occurs from negative 1.5 to negative 1, and from 0 to 1. And that's answer choice D. Small note here, the only reason that negative 1.5 is excluded from the interval, the reason we're using an open bracket is because it's an open interval. So we would never include negative 1.5. That's why it's an open interval there, even though the function would still be concave down at that point. I said I want to look at the potential for another solution path. Here's the graph of our first derivative here. Oh no, excuse me, this is the graph of the second derivative. Let me graph the first derivative. So probably, honestly, the fastest way to do this, if you had a calculator for this portion, which again, for your final, you will have a calculator for all parts. So that was our first derivative. Let me double check. -2. All right, so if I just look at the first derivative, I know I said that I would be concave down. Well, my first derivative is decreasing, and it's pretty easy to see that's happening from negative 1.5, the end of our interval. We center us on that. Cool. All of this is decreasing, f prime is decreasing all the way to -1. All right, so from negative 1.5 to -1, we've got a decreasing first derivative, so we're concave down. It's increasing all the way through here until we get to 0. And then from 0 all the way to 1, we are decreasing. So we could have just graphed our first derivative and taken a look at that. Or if we had taken the second derivative, we could see where that's negative. Again, second derivative, that's negative all the way until we get to -1. And then it is also negative between 0 and +1. These would be excellent ways to check your work, doing whatever's fastest first. Second to last problem, number 24. Given the graph of f prime, the derivative of f shown up above. Telling what your graph is probably the most important part of starting a problem like this, and a good annotation. Where does the function have a local maximum? All right, important thing to note. If f has a local maximum, I think we've said this at least 5 times today, that means that f prime of x is going to change sign. And again, let's just doodle it over here. There's my local max. My slope was positive here. Positive. And my slope was negative here. So my first derivative will be negative to the right, positive to the left. So f prime of x changes sign from positive to negative. So where does that occur on our graph? Well, let's start with where we're positive. Here we go from negative to positive. That's not what we want. We want positive to negative. So we're positive all through here. And then right at x equals 1, our graph of f prime goes from positive to negative. We'll do that in red. So at x equals 1, we have a local maximum. Answer choice C. Last problem. This one requires us just to remember what our mean value theorem is. There's actually no math that we have to do. We're told that a function is continuous on a closed interval. We're given the closed interval. We're told what the function's value is at both ends of the closed interval. G of 1 equals 5, G of 4 equals 8. And we want to know of the following conditions, which would guarantee that there exists a number C in the open interval, in the open interval, such that G prime of C equals 1. So this is a mean value theorem problem. I'm going to rewrite it just so that we have it to help us with. So G prime of C, I know is going to equal G of 4 minus G of 1 over 4 minus 1. Now, before you start plugging in numbers, recognize that we're given everything. I guess I could have written the more general form. G prime of C is going to equal just G of B minus G of A over B minus A, where A and B are our endpoints on the interval A comma B. But we just need to ask ourselves, hold on, what condition has to be true in order for this to work? What does have to be true? Well, we need to be looking at a closed interval here. We need our function to be continuous on a closed interval here. We want to guarantee a number on the open interval 1 to 4. So we've got the open interval checked. Provided with a closed interval. And we're told that the function is continuous, right? G is continuous. So that should be everything, right? We're all done here. If you carefully memorized your mean value theorem, which you should for your final, you'll probably notice that we are missing a condition. And actually, you don't even need to memorize the mean value theorem to know this, that we're thinking about something that has to be continuous, but also differentiable. That is one of our tenets, right, of our mean value theorem. And you might remember well that if something is continuous, that doesn't make it differentiable. Continuity does not imply differentiability. Why? Because something could be continuous, like maybe this guy with lots of different cusps, but we're not differentiable here, 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 or here. That's a big problem because the mean value theorem, all that it really states is that if I'm in some closed interval and I've got a function which is continuous and differentiable, it's nice and smooth, no cusps, no breaks, it's continuous, and no cusps because it's differentiable, then at some point, my instantaneous slope is going to equal my average slope. Here's my average slope between the two endpoints. And somewhere along the graph, at least once, looks like in the example function I drew, it occurs here, you're going to have an instantaneous slope that matches. But we need our function to be differentiable. Otherwise, we can't do the G prime part, can't take a derivative, something is not differentiable everywhere. So let's scan our conditions. Increasing is not a part of the mean value theorem. Differentiability, bingo, it's option B. Maximums don't matter for the mean value theorem. Don't care about horizontal tangents on that open interval. That's not necessary. Neither is decreasing. You could also kind of just reason this one out. It's a pretty easy process of elimination, but there's the rigor behind it. And that is all of our multiple choice questions for this practice final. See the other video in our playlist where Mr. Bartholomew will walk you through the free response questions. Happy studying.